Can you hear me now? All right, so testing 1, 2, 3. Oh, I can hear myself, and I'll just continue. So I want to thank you all for the feedback. I just switched something on my controls here. So there's no shortage of glitches to deal with on a new system. So thank you for the feedback, and please feel free to give input. Bread of Life, Rebecca, I actually invited her to, because she's a co-host on, going to be some of my flagship videos on eukaryotic evolution. She expressed the fact she didn't like the audio as well through Zoom, which is what I'm using. Zoom is tied to StreamYard, which is tied to YouTube Live. And so there are layers and layers of software to implement this show today. So if you don't like the quality of the audio, that's, any feedback on the technical aspects of what you see and experience is valuable. She did not like my fake background here. I have there are 2 standard TIE fighters and an advanced TIE fighter there in the background. Sometimes I have other backgrounds that include like scenes of the shore. So it gives me a little bit more flexibility to have backgrounds, but it does look a little fakey. So I want to thank everyone who's here. One thing I can't do, or I haven't figured out how to do, is to highlight comments on the screen like you do on StreamYard. So that's something I need to talk to people like James Coons or Praise I Am to teach me how to do that on Streamlabs. So those are just some opening remarks. Welcome to the Evidence and Reasons for the Christian Faith video channel. Most of you know who I am. I'm Salvador Cordova. I'm an independent molecular biophysics researcher. Prior to that, I was a senior engineer and scientist in the aerospace and defense industry. I have 5 degrees in engineering, physics, and biology. So it's kind of a funny road how my life transpired this way, because many people that know me personally view me more as an artist. I'm a very expressive person. I love music. I actually studied piano full time before I switched to engineering, and I wanted to be a novelist. So my life God did not choose a path for me that was kind of a little bit more native to my temperament. And people have said, Sal, you're going to struggle if you do science because you're not wired for it, and I'm not. So that means science is torture for me, and I'm going to torture. I call this session a nerd torture session. One of the ideas, if proven true on a scientific, empirical, theoretical basis, if proven true that the universe, or at least the Earth, or at least the fossil record, is young, let's say less than even 1 million years, if we can establish that, that would lend credence to a belief in a creator, but especially the creator of the Christian faith. So what this show is about tonight is really looking at the evidence that the Earth is young, or at least the fossil record is young. An important problem with that is the proportion of radioisotopes that are distributed throughout the fossil record and throughout the Earth. The mainstream says this is an indication that the Earth is old. And there have been many things put forward on both sides of the creation-evolution controversy that have said that, well, radiometric dating is unreliable. The creationists will say that, but then they'll go back and say, well, maybe it's sometimes reliable, like when we find carbon-14 in fossils. So it's a little more subtle. But then they'll say, well, there's an appearance of age, but it's not real. There was accelerated nuclear decay. And the evolutionists will come back and say, well, that causes a heat problem. If you accelerate nuclear decay, it's going to kill us because we have potassium isotopes in our body. Even a slice of bread will kill you, and then your blood will boil if there's accelerated nuclear decay. And I've actually said, creationists, I think the evolutionists this time got it right. The accelerated decay, one, we have no, let me qualify that. It would be called isotropic accelerated nuclear decay. And that's just a fancy word. I don't know where that term really comes from. They could just say universal decay. That means at some time in the universe, during Noah's, especially during Noah's flood, in connection with it, the universe suddenly started accelerating nuclear decay all around the universe. And if it deals with some of these things called the strong and weak nuclear forces, this could just blow apart the universe. So I've said, I think creationists, to my creationist colleagues, the majority of them accept accelerated nuclear decay as an explanation. My internet colleague, Erica Gutzik-Gibbon, she and I are on extremely good terms. We've agreed never to debate each other because we have a history of just really good friendship on the internet. It's kind of hard to explain how we're not at each other's throats. But for any of the Christians here, and this channel does cater to certain Christians who are science students in college and graduate school, we tend to be just look at other graduate students like Erica as our friends and colleagues because they're suffering through school just like us. And so it's just inherent that we just tend not to be at each other's throats. We're here to support and comfort each other. Reason to Doubt, who's Jordan K., he says, who could have a problem with Erica? She's awesome. Yeah. So Erica and I, we're on good terms. We have a history. We promise not to debate each other because our friendship is more important. And she's pointed out, and really, I have to give credit to Jordan K. here, that there's going to be problems with accelerated nuclear decay. And the majority of creationists, the overwhelming, will say, no, it just happened. You'll hear that gentleman who's a retired geologist from my school, something. I forgot his name. I'm so sorry, sir. McQueen. I think his name is McQueen. It's not Steve McQueen. It's another Professor David McQueen at George Mason University, which I'm a little, this is a little funny. He was actually professor at George Mason when I was an undergrad there. And George Mason is a creationist factory. Just Charles Jackson went there. 3 PhD biologists graduated from there. Gordon Wilson, Timothy Standish, Timothy Brophy. There's a professor, I.D. Friendly, and Carolyn Crocker. We had 3 professors who were physicists that were against the Big Bang. I mean, yeah, it's just a crazy place. Last but not least, there's me. Came from George Mason. That was my undergrad. And David McQueen invokes accelerated nuclear decay. And Erica rightly pointed out, and she gets this, I know from people like Jordan K. and others, that you can't just throw a miracle in there and say it's still science. And I would actually argue that miracles formally are outside of science because it's not repeatable. It doesn't mean that they're not true. You just can't repeat some of the things experimentally. Secondly, there's that heat problem. And so do you invoke, you're actually having then to invoke 2 miracles. There's some ways to alleviate this a little bit because the distribution of some radioisotopes are not, it may not be uniform, but you'll still cause your blood to boil if you accelerate nuclear decay. And am I being too harsh on my fellow creationists? I don't think so, because it's in the rate book and also other creationist publications where it's mentioned in passing the potassium, I believe it's the isotope 40, potassium 40 problem. Correct me if I'm wrong, anyone. If there's accelerated nuclear decay, it'll kill us. And I said, okay, that's a deal breaker. It's time to just move on, guys. Maybe this isn't the path. And there's been a minority of creationists that have invoked change of nuclear structure through other means. And in the last, it started, I began to investigate that. And there are a variety of reactions, some that are very high, that are high energy. So I'm just going to roughly define this. Low energy is like your light bulb, on the order of electron volts per photon or per particle. Higher energy would be like in the tens of thousands, or I call it intermediate energy, would be tens of thousands of electron volts. That would be like X-rays. And I would kind of class high energy in the millions of electron volts. I don't know that anyone adopts that, but just for the sake of the way that I discuss it, I will say, low energy is on the order of tens or less. Intermediate energy, tens of thousands. High energy, millions. And I may, flip between them. We're finding out there are high energy reactions that are not strictly like a thermonuclear fusion. You can change nuclear structure through lightning, and that's been confirmed in 2017, and then numerous other experiments, but that's still a high energy reaction. And we have what I call intermediate energy reactions, where you could change mixed energy nuclear reactions, where you have one part of the system that's practically, cold, and the other part is hot. And that would be systems like pyroelectric fusion. And then NASA's been doing a lot of mixed energy reactions where one part of the system is basically room temperature, and then you have these higher energy particles interacting. We know now that when there's tectonic activity, it's getting more accepted that when there's tectonic activity, you can generate electricity that would at least be able to create high energy nuclear reactions, and maybe even intermediate energy nuclear reactions. Where I think there could be a lot of interest is low energy, truly low energy nuclear reactions. We have had just a handful of mainstream accepted low energy nuclear reactions. One of them I've talked about is Muon-catalyzed fusion. So can we do that in the solid state? And I'm going to propose, actually it's not, I off the cuff, maybe a couple weeks ago had suggested instead of muons, how about quasi-particles? So why don't I read what quasi-particles are? And because they sound like science fiction, but anyone who's an electrical engineer, and Ben Rex, I'm thinking of you, the Silicon Valley here in the United States and the chip manufacturing industry, transistor manufacturing industry, leverages quasi-particles. One of the most famous quasi-particles is called the electron hole. And what a quasi-particle is, and I'm going to go a little bit more into this, are they actually real or not? And some people have argued in the strictest sense, all particles are actually quasi-particles that emerge out of the quantum foam, which is kind of a very interesting way of looking at things. But and then there's also kind of like the more pragmatic way of dealing with quasi-particles, where we say, well, in the condensed matter state, condensed matter would be liquids and solids, but especially in solid, in the solid state, you can model these, the collective behavior of all the molecules there as if they created kind of a particle that is both, that has position, size, and inertia, or quote unquote mass. I think inertia might be a better term. And so it has all the characteristics. You can model it. This was done actually to kind of simplify the analyses of what they call an n-body problem. When you have a solid with all these bazillions of molecules and you're trying to capture how this behaves, it's like the math got intractable. But they realized quantum mechanics can sometimes give you a little out, that you can model the collective behavior in some localized situations as quasi-particles. And these quasi-particles have position, size, and inertia, quote unquote mass. So, which then would translate, if you have position over time, that translates to velocity. Velocity times the mass, or inertia, is the momentum. So it has momentum, it has mass, it has size, everything that you would want to describe a particle. So in electrical engineering, we have the electron holes, which are positively charged particles, quasi-particles. In biology, in my biochemistry textbook, and I didn't have time to show it here, in the photosynthesis system, or at least in plants, I think it's photosynthesis, the plants implement a quasi-particle called excitons. So let me try to introduce quasi-particles a little more. See if I can put this up here. And let's see. And Sandy Pigeon's here. So great to see you. And what did I do? Boy, I messed that up real fast. Okay. Another technical disaster here. Let me try to get this going a different way. See if I can get it going a different way. Let me turn this off. Okay, I know what I did. Hang on. Apologies. I'm learning how to use this system. And I'll just put myself up here. And let me expand this so everyone. I'm just going to read. I'm not going to read the whole article. So the near magical mystery of quasi-particles. Polaritons, which are half light, half matter quasi-particles, emerge in a simulated lattice of particles cooled to a few degrees above absolute zero. And I can't pronounce his name. Waking up in an alternative reality, Harry Kim, an officer aboard the starship USS Voyager, creates a distortion in the space-time continuum with a beam of polarons. Sounds like science fiction? Science fiction? Well, yes, but only in part. Star Trek used to love taking the names of real quasi-particles and ascribing magical properties to them, said Douglas Nadelson, a physicist at Rice University in Texas, whose job involves creating actual quasi-particles with near magical properties. Quasi-particles are kind of particles. Barred entry from the exclusive club of 17 quote-unquote fundamental particles that are thought to be the building blocks of all material reality. Quasi-particles emerge out of the complicated interactions between huge numbers of those fundamental particles. Physicists can take a solid, liquid, or plasma made of a vast number of particles, subject it to extreme temperatures and pressures, and describe the resulting system as a few robust particle-like entities. The emerging quasi-particles can be quite stable with well-defined properties like mass and charge. Polarons, for instance, discovered by Lev Landau in 1933 and given a cameo on Star Trek Voyager in 1995, materialize when many electrons are trapped inside a crystal. The push and pull between the electron and all the particles in its environment dress the electron so that it acts like a quasi-particle with a larger mass. In other types of condensed matter that have dominated research over the last few decades, things get a whole lot weirder. Researchers can create quasi-particles that have a precise fraction of the electron's charge or spin, a kind of intrinsic angular momentum. How these exotic properties emerge is still not understood. It is literally like magic, says Sankar Das Sarma, a condensed matter physicist at University of Maryland. By the way, this is just what I call cool physics. Using intuition, educated guesswork, and computer simulations, condensed matter physicists have become better at figuring out which quasi-particles are theoretically possible. Meanwhile, in the lab, as physicists push novel materials to new extremes, the quasi-particle zoo has grown quickly and become more and more exotic. It really is a towering intellectual achievement, said Nadelson. So let me just look. I'm going to turn here and look at the side chat because I think this is going to raise interesting discussions. I'll tell you how there has been a significant experiment. They now have quasi-particle colliders, and they weren't sure that they could actually do this. So you've heard about the Large Hadron Collider, and then they tried to build this super collider in the United States with billions of tax dollars, which I thought would have been cool. That would have been an interesting investment of money. And they have said, well, can we build quasi-particle colliders? And I have an article from the prestigious, it is a summary of something in the prestigious scientific journal Nature. Let me see if I can see if Streamlabs will let me put this up. Let me give it the old college try, as they say. Let's see if I can get it going here. Again, thank you for bearing with me as I'm on a new system in StreamYard. All right, so okay, I'll turn this off. Let me know if you can all still hear me. So there's this thing called the quasi-particle collider, and let me so whether or not one sees any relevance of this in young Earth creation, this is still really cool science, quasi-particles, but now we might be able to combine quasi-particles to give an explanation for cold fusion. So the quasi-particle theory, we have this quasi-particle collider. It was reported in May 2016. Scientists proved that basic collider concepts from particle physics can be transferred to solid-state research. And in the early 1900s, Ernst Rutherford shot alpha particles onto gold foils and concluded from their scattering properties that atoms contained their mass in a very small nucleus. 100 years later, modern scientists took that concept to a new level, building the Large Hadron Collider in Switzerland to smash protons into each other, which led to discoveries I don't know if you could still hear me. Zoom just quit on me. Hang on. I'm just going to continue reading. Which led to discoveries of the Higgs boson. However, what worked for particles like the Higgs hasn't translated to solids until now. Okay, so thank you, Reasons to Doubt. I'm going to try to come back online on Zoom. You just can't see me right now. However, what worked for particles like the Higgs hasn't translated to solids until now. Experiments conducted by UCSB physicist Mark Sherwin and an international team proved that basic collider concepts from particle physics can be transferred to solid-state research. Their findings appear in the journal Nature, which is the #1 science journal. Ultimately, this approach might lead to a clarification of some of the most outstanding enigmas of condensed matter physics, said co-author Sherwin, director of UCSB's Institute for Terahertz Science and Technology and professor in the Department of Physics. This is a fundamentally new concept that could lead to better designed modern materials. Our results also may one day provide a better understanding of important phases of matter, such as those found in high-temperature superconductors. Okay, I need to take a pause while I try to resolve the technical difficulties. I'm going to be trying to talk and chew gum, so to speak, as I try to get this going. I'm trying to get my camera, my Zoom system going again, and I need to restart my meeting, and I'm going to have to do some crazy things to get it going. If you'll just indulge me. And I'm learning some skills on the fly here. Okay, see if my Zoom is going to come up. So in the meantime, let me just, it's going to take a while for the software to spool up. So I want to thank everyone for their forbearance. I'm going to just look through the side chat here. So there's some greetings. I see Bread of Life, Rebecca, she dropped in earlier. Mark O'Connell. Redeemed Team, greetings. Mitchell, Jesus Garcia. Reasons to Doubt, with Jordan K. Sandy Pigeon. All right. Half light, half matter. Yeah, particles, quasi-particles are insane. The thing that I think is significant is, okay, let me see if I can come back online, see if it's gonna, hopefully I get the window back. Nope. Oh, all right, I think I'm back. The thing about this collider is when the two quasi-particles collided, it caused a burst of light. So I'm just going to repeat that again because this is significant. When the two quasi-particles collided, it caused a burst of light. So this can be modeled like a discrete event. And so this is really amazing. You can have a collective system create discrete quantum events. A photon release is a quantum event, a discrete thing. So usually, like when we had the photoelectric effect, when an electron jumps from one energy state, from one quote-unquote orbital to another. My physics and chemistry friends are going to get on me if I misstated that, so just feel free to correct the terminology. When they change, when they transition from energy states, you get a photon release, a release of, in some cases it'll be visible. In that case, we call it light. Albert Einstein actually won his Nobel Prize not for general relativity or Brownian motion, but for the photoelectric effect, where he deduced that the photons are released in packets through this photoelectric effect, where there are transitions in the electron state, the orbital state. Now, Planck realized this thing of black body radiation, where we have an entire system also giving off, well, after Einstein, we realized then the black body radiation is the system giving off discrete packets of energy. So in the condensed matter state, you can have discrete quantum events. And now we can even see it with quasi-particles colliding. When they collide, there's this release of energy. So they're physicists actually, who they keep thinking about grand unification. The quasi-particle stuff is kind of a little unsettling because then there's like saying, well, there's no unification. It's just anarchy out there. And so some physicists like that we can just concoct all these particles. And then there's a theory then that maybe, you know, everything's a quasi-particle. So it depends on who you talk to. Okay, so it'd be kind of unsettling. I mean, we'd like to think electrons are stable, you know, and not something that just kind of pops out of nowhere. So I'm not going to get too deep into this kind of esoteric, but the fact we can collide quasi-particles and get an energy release, that's really cool. And as I said, the semiconductor industry uses quasi-particle theory to describe the movement of electron holes. I mean, all of our computers are driven by quasi-particle theorists, so to speak, out there in Silicon Valley. In biology, we're studying the use of excitons that are very short-lived, and they are able to, the plant uses them. So there's a lot of leveraging in biology of quasi-particles. There may be a lot more leveraging than we realize, because now we're starting to study this. So what's the topic about tonight? There has been an intense debate about low-energy nuclear reactions, particularly low-energy fusion, what they call cold fusion. We have verified experimentally muon-catalyzed fusion. A muon is one of those special particles that don't last long. We're bombarded with them all day, small amounts. And when you can get the muon in the proximity of like either a deuterium or hydrogen nucleus, you can cancel out its charge, and then it enables fusion to happen at room temperature. This is well accepted mainstream science. It is cold fusion, but the term cold fusion got a very bad name because there have been some charlatans claiming cold fusion. There have been some charlatan theories, unfortunately, try to explain the mechanism. And then there have been maybe some good experiments that just couldn't be repeated except under very special conditions. And so where it began to get the very bad reputation was the Pons and Fleischmann experiment that very few people could replicate. They therefore concluded it was a fraud, and the reputations, professional reputations, were damaged. But chemists around the world have been finding anomalous results consistent with this. Now, one of the pioneers of muon-catalyzed fusion, which is absolutely mainstream, was Stephen Jones. He began working on other experiments and arguing he's seen evidence. So he has the laboratory skill, at least to detect if transmutation happened. And he claimed that he got results of low energy fusion. But by that time, the community was very negative on this, very hard to duplicate. What has heartened me is we've had a lot of mixed energy reactions, which is a closer step to at truly low energy. We've had a lot of mixed energy nuclear reactions. The other thing is we're having more experimental results. Chemists around the world are just scrambling. And as I said, this is interesting physics, interesting chemistry. And if we can do, and there's a scientist, Vostoysky, in Ukraine. God willing, he still survived the siege of Kiev. He's the department head of physics and in radiological physics at Shevchenko University in Kiev, Ukraine. And he has done research on biological organisms that he claims can transmute. I'm indebted to Jordan Kay for examining his paper. He found some things that were concerning, and just in this for the sake of full disclosure, I had to agree. I said, yeah, there looked like some sloppy mistakes. But I have read some of Vostoysky's work, and the physics was just blowing me away. I said, this guy is, at the very least, very well schooled. Maybe his papers are sloppy. So, what I say is the way to resolve this is with more experiments. I have since looked at experiments that are happening in the United States with high energy, high density electrons. Vostoysky and Adamenko claim to be able to transmute substances using high-density electrons, and they cited the inspiration of their work was the an alternative nucleosynthesis process in stars, rather than kind of neutron stars or these high-powered stars creating elements through the Big Bang, which I don't accept, but let's just say accept it for the sake of argument. They are saying that the electron density could be high enough you get something called quantum attraction, where the charge is irrelevant. Now, I did a show on this where I walked through Adamenko's paper. It was like way over my head. I mean, I'd have to be studying this for like 2 or 3 years full time to get a grasp of this. Thankfully, I'm in touch with mathematical physicists who are young Earth creationists. They're quiet. For the most part, they're quiet. One of them is more well known, and that's Philip Dennis. He's published in the American Physical Society, the Physical Review Letters, and they may be able to help me through some of this. So it seems there is good theoretical and experimental verification. We could have high-density electrons and reduce the Coulomb barrier and then have fusion, but it's still a high-energy reaction. So this, a minority of young Earth creationists like Walter Brown, Brian Nichol, and myself had said this is probably one avenue of changing nuclear structure. Now, will that solve kind of the proportion of parent and daughter products? And Jordan K. has rightly pointed out that, and also Mr. Jetty, who actually works on a particle accelerator, he's part of our community here. He works on microtron particle accelerators. He said, even supposing that Adamenko and Vostoysky are right, this may not solve the radiometric dating problem. It does give an avenue, possibly, however, of changing nuclear structure. So where was I headed with that? I said, okay, let's just look at low energy stuff. I said, if we can get a quasi-particle called the heavy electron quasi-particle that behaves a little bit somewhat like a muon, then we might be able to affect a low energy nuclear reaction at room temperature. And so that got my interest. And I mean, that was just a speculation. And I said, why don't, a couple days ago, I said, why don't I just Google this? Maybe great minds think alike. I'm just kidding here. Maybe someone else has thought of this. And lo and behold, I found a paper that is, it's in preprint, it's in archive. That means it's not been published in a mainstream journal. But it was still a really good article. It was not written, to my knowledge, by creationists. It's written by people that want to build cold fusion reactors. And so there are cold fusion reactors. We just haven't been able to make any that can give us extra energy reliably. Although that raises an interesting complication for society. If we end up all driving cars with nuclear reactors in them, that would be interesting. And since we're worried about nuclear proliferation, that raises other implications. It could be really the end of civilization if it gets too powerful. So I'm just going to defer that discussion for another day. But as far as young Earth creationism is concerned, we don't need low energy fusion reactions. We just need, we don't need nuclear reactors, low energy nuclear reactors. We need low energy fusion reactions that you may need excess energy to make this feasible. So now I'm going to propose the mechanism for, this is the most credible paper to date, I think, that tries to explain the theory of low energy nuclear reactions using electron quasi-particles. There are other theories like Whiteham-Larson, which has been discredited as far as I'm concerned, and there have been some electron screening theories, but this quasi-particle one I like. So now we're actually going to get to the meat and potatoes of tonight's stream. I have been on air now for 45 minutes just explaining what quasi-particles are, because I knew, even for me as a physics student, I barely got any quasi-particle theory even when I was taking solid-state physics. It's a tough field. So let me now try to bring up the quasi-particle paper and see if I can get it. Oh wait, maybe it's this one. Let me turn this one off. I have all these windows I need to be flipping through. Okay, I'm going to turn off some windows here. Okay, a little better. And Sal, look out, Imperial forces are right behind you. Thank you. Yeah, they're on my 6. Okay, so for those who joined late, I went into 45 minutes talking about quasi-particles. We have now quasi-particle colliders. Quasi-particles drive the Silicon Valley, the computer, the chip industry. Electrical engineers like Ben Rex would probably recognize the idea of electron holes. But there's a whole suite of quasi-particles, even in biology, called like excitons that are critical for for the process of photosynthesis. We have a quasi-particle collider where we get quasi-particles to collide with each other. And now we're looking at quasi-particles being used to lower the Coulomb barrier to affect low energy transmutation in the nucleus, otherwise sometimes known as cold fusion. I have said that cold fusion has been verified with real particles like muon-catalyzed fusion that is accepted in the mainstream. It's just that the word cold fusion has just really bad connotations, but it's been verified to happen with muons. The question is, can it happen in the condensed matter state without exotic particles like muons? And so the alternative is potentially quasi-particles called heavy electrons. So now I'm just gonna cover this paper and read it end to end. And now the nerd torture begins. Bwahaha. Okay, so let's see if I can get this. Okay, the title of the paper is Catalysis of Transmutations by Heavy Electron Quasi-Particles in Crystallites. Anthony Zuppero and Thomas Dolan. Thomas Dolan is University of Illinois Urbana-Champaign. That has been the site of professors that are working on Adamenko's high-energy nuclear transmutation experiments with high-density electrons, and I described that experiment in one of my other shows. And then there's this Applied Research Corporation. They are trying to build cold fusion reactors. And you could see, okay, this is 27 pages. We may not be able to get through all of it, but we'll just plow through as much as we can. This article describes our hypothesis. Let me make sure, okay. This article describes our hypothesis on how transmutations may be induced by solid-state effects in a crystalline lattice. We discussed the chemical reaction case, our extension to the nuclear binding case, and a tri-body model of a heavy electron quasi-particle catalyzing the binding of two nearby ions. For a given primary reaction, we can estimate the required electron mass threshold, identify possible reaction products, estimate tunneling probabilities, and calculate energies available for each path. We compare model predictions with experimental data of transmutations and consider hazards associated with experiments. Like explosions, yes. Scientists have been reporting nuclear transmutation and anomalous energy generation accompanying chemical phenomena for 30 years. Hydrogen and deuterium apparently can enable nuclear transmutation of reactants that generate elements and isotopes that were not originally present. The isotopes provide the key clues to understand the process. The energy generated exceeded the available from chemical reactions, inspiring worldwide interest. Storms 2014 provides abundant background information, and Biberian 2020 describes the current state of research. Our hypothesis derives from a chemical... Okay, let me just time out here. People are skeptical of the research. This research is continuing to move and be funded. And let me see if they have Kuber's graph. Let's see if they have it here. I don't know if it's in here. Let me just see if it's in here. The thumbnail had the graph that showed, there it is, right there. So there have been a number of laboratories that reported this. And what's important is helium is a byproduct of a fusion reaction. And so you would expect that if you have more heat generated by the reaction, you should be generating more helium. And this just requires some careful measurements. And all the dots there, I'm presuming, and correct me anyone if I'm reading this wrong, all the little crosses there are like the error bars, and in the center is a little circle. So each of the crosses represents a separate experiment. And you could see that as we have more heat, as we have a helium increase in parts per million of volume per volume, there's an increase in heat. And let me just move my, so you could see kind of the axes there. And so this is one thing, is we are getting replication across laboratories. We also have all sorts of very careful instrumentation to detect if there's been changes in the proportion of isotopes after the experiment. Or even better is when you have an isotope that wasn't even there and then trace amounts show up after the experiment is conducted. And so you need some really good chemists to detect this. So again, the argument is not whether cold fusion can happen, but whether it can happen in a condensed matter context. So I just wanted to cover that. So this is why this motivation keeps happening. And then I cited in earlier shows the mixed energy reactions. So I call those MEANers, mixed energy nuclear reactions. These are LEANers, low energy nuclear reactions. Mixed energy nuclear reactions, definitely high energy nuclear reactions happen. Mixed energy nuclear reactions are now confirmed, accepted in the mainstream, published in mainstream high profile journals like Science and proceedings, reports by NASA. So mixed energy nuclear reactions, we're going from high energy to mixed energy. The goal is to get into low energy nuclear reactions, which are called LEANers. So I joke, I say, okay, these shows are about LEANers and MEANers. So let me continue. So they just said scientists are reporting low energy nuclear reactions. Now I'll just skip. Our hypothesis derives from a chemical physics binding reaction discovered during the 2000s. Researchers at UC Berkeley and UC Santa Barbara discovered a binding reaction referred to as vibrationally promoted electron emission, VPEE, by LaRue et al. Chemicurrent by Nienhuis, and nanodiode by Somarji, G. Zupiro, Gidwani et al. Now, if that is the same, let me just verify. This could be, let me see, Zupiro. So the guy that was actually at UC Berkeley and Santa Barbara, that might be the same Zupiro. He was actually then involved in the experiments at UC Berkeley or Santa Barbara that found this VPEE phenomenon. LaRue documented that when reactants attracted to electrons between them begin as almost totally separated entities, and when the electron effective mass satisfies a simple function of binding and Coulomb energy and reaction product size, the tri-body is unstable and promptly collapses and binds. The binding energy becomes partitioned into the kinetic energy of a liberated ejected electron and the internal vibration of the reaction product. Okay, I don't quite understand what that means, and that's just par for the course of reading a technical paper. The discovery quantified the condition where a certain type of tri-body reaction undergoes a very fast and prompt binding, and the energy can be all in the electron, all in the reaction vibration, or mixed. For example, in the chemical physics case, a highly vibrationally excited molecule may attract an electron from a metal surface, transfer most of the vibrational energy to the electron, and then eject it, or CO, which I believe is carbon monoxide, may bind to oxygen on a conducting surface, ejecting an electron with binding energy. Shapiro and Dolan, 2009. Okay, so they've published on this. I'm assuming in mainstream. We'll look at this. I can look at that. We postulate that a similar reaction may occur on the nuclear scale, which can have a similar potential energy curve. We substitute nuclear binding potentials for chemical ones and add known solid-state heavy electron physics, which is really cool. Okay, now you're getting somewhere, guys. Now let me just take a pause and look at the side chat here. Okay, so I'll just continue. Some reactions appear to bind pairs of protons or deuterions or other light nuclei to heavier reactants as if catalyzed on the surface of a crystalline lattice. The reactants include calcium, Ti, titanium, anion, nickel, I think, Sr, don't know what that is, Sr. PD's palladium, Cs, I think is cesium, VA's barium, W, oh, I don't know what that is, and U, and radioactive isotopes. The reactants include, oh boy, it goes all the way up to uranium. That's cool. The low mass isotopes may include hydrogen, deuterium, tritium, lithium, sodium, and potassium. K is potassium. So we can react heavy isotopes, and uranium's a heavy isotope, and radioactive isotopes, and then react them with low mass nuclei like hydrogen, deuterium, tritium, lithium, sodium, potassium. Only trace neutrons and gamma rays are observed. And just as an aside, this is where there's been a lot of debate. Why aren't we getting gamma rays in the process of this reaction? And let me just pause here. The prevailing theory among the leaner community is that rather than gamma rays, the reaction releases the energy from the nucleus in multiple photons that are much lower energy. And that's how you're able to get excess heat. So this would be, oh, thank you, Mark O'Connell, Sr is strontium. So that you still get the energy released, but it's not in gamma rays. It's in smaller multiple packets. What would be interesting is if they can correlate the supposed number of nuclei that fused and the energy release with their calorimetry and the excess heat. That would be, I don't know if that anyone has actually done that and said, okay, the accounting at least works. If we're not getting gamma rays, we're at least getting the right conversion in terms of energy. So as far as I know, for me at least, it's an open question. I don't know if anyone's actually done that. The story of neutrons is another one, and we'll just keep plowing through this. Only trace neutrons and gamma rays are observed. Almost the entire periodic table could apparently take part in electron quasi-particle catalyzed nuclear transmutations in appropriate lattice conditions. Let me repeat that because this is relevant to young Earth creationism. Only trace neutrons and gamma rays are observed. Almost the entire periodic table could apparently take part in electron quasi-particle catalyzed nuclear transmutations in appropriate lattice conditions. And if that's the case, let me try to get this straightened out. If that's the case, this provides an avenue for an alternative to the heating problem of young Earth creationists. They can just dump accelerated nuclear decay and then maybe consider quasi-particle transmutation at low energy, and we still have the option in our pocket of high energy nuclear reactions that are lightning induced, but these are high energy. Again, high energy is in the millions of electron volts. Low energy is in the tens or less of electron volts. And so your light bulb operates, the photons from your light bulb operate in the under tens of electron volts. X-rays are in like the tens of thousands. And then in lightning strikes, the activity is in the millions of electron volts. We could, this would be a very, okay, independent of young Earth creationism, this is just really cool physics, all right? So I'm trying to deliver something that, you know, I think that if everyone can walk away from this discussion and feel that they've at least learned something, that they've learned about quasi-particles in condensed matter physics, that they've learned about quasi-particles colliding and causing these energy bursts. I think we've at least moved forward. And then now we're considering the use of electron quasi-particles to change nuclear structure. To me, this is just a new frontier. For anyone, independent of whether you're young Earth creationist or not, this is just really cool physics. And so I'm honored to have this chance also to have an audience that would be interested in this sort of thing. And Brainbug, by the way, greetings, and Patrick Alexander joined us. So let's just continue on. One of the reactant ions may have any number of positive charges. Molecular reactants can bind chemically due to chemical binding potential. Nuclear reactants can bind together with nuclear binding potential if the tri-body can contract to a size close enough to the nuclear force radius for binding to occur. To contract to this size, electron tunneling must occur. Okay, this is some quantum mechanics here. All right, I'm not saying that I totally understand this, but I understand the physics enough to know this guy isn't BSing. This is already, this has the aroma of good physics. And one reason I'm presenting it, guys out there that may remotely be interested, you can look at this and say, hey, Sal, this is good, this is bad, this sucks. So, you know, if I don't get the usual Tuesday lampoon of me reading this paper like they did for Kent Hovind's dissertation, then at least that's the first heuristic. All right. So this is going to be interesting where they compare real electrons with quasi-electrons. The quasi-electrons have the right size to allow the reaction. And so that was the one piece that I got. Say, quantum kinetic energy of confinement. And I'm just going to read through this, and none of us are going to understand it, but, you know, maybe I found that if we just keep reading it and, you know, we say, okay, these are all areas I don't understand, I can go read other papers to teach me. So just, that's how we learn. That's how I learned a lot of biology, just reading papers I didn't understand, and I could come away with a little bit more knowledge, and then I'd ask people that do know, or I'd take classes, or I'd read other papers, and then I start to learn. So this is part of the learning process. Quantum kinetic energy of confinement. We use a one-dimensional tri-body model with an electron quasi-particle and a molecular or nuclear binding potential between a single positive and a multiple positively charged reactants. So again, the readers of this, the audience they're writing to, they expect the audience to be familiar with this, and obviously I'm not. So I'll just plow through this. Even though the net Coulomb attraction in solid materials is attractive, and there are no net repulsive forces, the electron's quantum kinetic energy of confinement, the QKEC, from the Heisenberg uncertainty principle, HUP, provides a repulsive momentum to resist collapse of everything to nuclear density. And I've mentioned it before, and I'm embarrassed to say this. Yes, I studied quantum mechanics, and I have studied nuclear structure in graduate school. And even at the end, I'm like, I can't actually write the math why the electron just doesn't go inside of the nucleus. I mean, the electron's negatively charged. The nucleus is positively charged. Why don't they just merge? Yeah, I get it. It's like in orbital mechanics, you have two attracting bodies. It doesn't necessarily mean that they're going to merge. Good example is the moon orbiting the Earth. So what one physics professor said is, okay, just kind of look at it like an orbit. The old Bohr atom, where the electron has a velocity and it's not going to merge because it has velocity. And that's not exactly, that's what they call the semi-classical quantum model, which was then superseded in 1925 by quantum mechanics with, I think it was Heisenberg, not Schrodinger. Okay, so they're formally describing then why regular electrons don't go into the nucleus. They appeal to this quantum kinetic energy of confinement and Heisenberg uncertainty principle, and it provides a repulsive momentum to resist collapse of everything to nuclear decay. So this repulsive momentum, I think, correct me anyone if I'm getting my quantum mechanics wrong, this is like when Dr. Trefl told me this is like the moon orbiting the Earth. It has velocity, but the moon doesn't drop to the Earth because it has enough velocity, it's just going to orbit. And so you kind of have the same thing, except it's not a discrete orbit. It's kind of like an electron cloud. Okay, so this is starting to halfway make sense. The electron energy associated with confining an electron to a region is the quantum kinetic energy of confinement. Kinetic energy is represented by KQEC, and I'm just not going to read that formula, P over P naught squared. I think that where P is the momentum and M star is the effective mass, and it's going to be greater than the variance in momentum divided by twice the effective mass. Okay, you have the formula there. Okay, so this is agreeing kind of qualitatively where we're just looking at like the moon orbits. This is just saying you haven't, when it says kinetic energy and you're describing momentum where momentum is velocity times mass, this again is it's like the moon orbit, but qualitatively by analogy. Okay, quantum mechanics is funny. So this is where it's bad, where I'm mixing quantum mechanics with classical mechanics, but we have to use classical mechanics a lot because our experiments at the macro level, we have classical measurements. And so we import a lot of classical concepts to quantum mechanics. And this is where it becomes, the duality of this becomes kind of obnoxious. And it's hard to decide when you're switching from classical to quantum. The ion separation is characterized by its variance sigma squared x, which is the measure of the size of the electron confinement region. And they go into detail. The Robertson-Schrodinger relation, modern Heisenberg relation, relates the variances of the momentum and position relative to the center of mass XO and the momentum P0. Okay, I'm just going to guess here where they're going, where they're headed, and I'm just going to subtract out the kind of the technical language. Regular electrons cannot go into the nucleus. That's where they're appealing to Heisenberg's uncertainty principle and that quantum kinetic energy of confinement, the KQEC. So therefore, the electron's just going to mostly, for the most part, hover outside of the nucleus. Its mean distance would be what we call, like, let's say in the s orbital, you can define kind of the mean distance. And I cited another article where occasionally the electron is in the nucleus. There's a small probability it will be inside the nucleus. But because, for whatever reason, it still does not merge into the nucleus. And that's kind of the nuclear physics I'm not familiar with. So how is it that can occasionally be in the s orbital electron can occasionally be in the nucleus and it still doesn't merge? Okay, so this is what they're addressing. Where they're going to go is to say, okay, let's have an electron quasi-particle. The electron quasi-particle can actually merge into the nucleus. That's the key. When it merges into the nucleus, it can then reduce the Coulomb barrier. You can have cold fusion. There's a probability then, an increased probability of having cold fusion with this. So all they're doing right now is they're just describing the parameters of a regular electron and saying, okay, this is why it doesn't happen. Then they're going to extend the math and say, okay, now we have an electron quasi-particle. It has different parameters. You're going to get a different parameterization of the Heisenberg uncertainty principle and the quantum kinetic energy of confinement. And this will all it's a long way of saying, this quasi-electron can be in the nucleus. It's not going to actually merge into, like, say, a proton and make it a neutron. That's not going to happen. But what it will do is reduce the Coulomb barrier, and now a proton can merge, a positively charged nucleus can merge with another positively charged nucleus. There's a small probability, but it is a higher probability than we normally get in ordinary condensed matter physics. And this would lend credence then that biological organisms can remediate nuclear structure. So I'm going to defer here to Jordan. Let me try to get to your comment. And by the way, Jordan, wishing you the best. I'm glad you can join my stream. And maybe we'll present your very fine work on Radha's paper, a creationist colleague. And it's a critical evaluation, but I think it's excellent work. And I, by and large, agree with Jordan. I'll at least provisionally accept everything that he says. So now he says, can you go over what a quasi-particle is again? A quick Google seems to indicate it's like the effective properties of an electron moving through some medium. Okay. A quasi-particle is not a real particle. So one way it's described in Botanica, if you look like in an air bubble, like when you're boiling water, it's not really a particle. It's more an emergent phenomenon, but you can model it as like a real particle in that bubble in the boiling water has size, it has position over time, so it has velocity. But it's not a real particle. It's a collection of particles. It's a collection of particles. Where the metaphor breaks down in condensed matter physics is that your collection of particles can actually be modeled as creating like a bubble, but the bubble can actually have subatomic size. So effectively, you have kind of a net behavior. Now, how this emerged, maybe I forgot where I read this. Let me look at the Wikipedia article, and I think it's actually, rather than Wikipedia, let me see if I could find this. Proceedings in National Academy of Sciences. Okay, this is a better description. And let me try to move this. I have this is a good question. This is why it's great to have a live stream in this case. Let me see if I could shut down window 1, activate screen capture 2, and let me see if I can. I would appreciate your forbearance here, guys. I'm still getting acclimated to Okay, rather than Wikipedia, I'm going to read this from the Proceedings of the National Academy of Sciences. So this is a very good source. I would deem this textbook worthy. Physicists have identified dozens of different subatomic species in the particle zoo, but most physical and chemical interactions arise from only three: the proton, the neutron, and the electron. There are a lot of those. Solids and liquids contain on the order of 10 to the 24th particles per cubic centimeter. Each of those quantum mechanical properties may interact with all the others in the material due to the long-range nature of the electromagnetic force, which adds up to one sprawling headache of a math problem for condensed matter physicists who want to study the properties of matter on the subatomic scale. The problem is particularly vexing for condensed matter physicists who study crystalline lattices or superconductors. Okay, so the idea is we're not going to calculate an n-body problem of 10 to the 24th. Forget it. They say, well, why can't you simulate this in a computer? It's like the best simulation is actually the physical device itself. You're not going to be able to model this. Enter the quasi-particle, a mathematical construct that makes near impossible calculations not only possible, but also straightforward. Decades ago, researchers realized that they don't have to tackle the many-body problem that arises from the messy interactions of real quantum particles. Instead, a crystal solid can just as accurately be studied and analyzed as an average bulk object along with a collection of quasi-particles. Disturbances in the solid that act just like well-behaved, non-relativistic particles that barely interact at all. They are fictitious and easier to work with, and their collective behavior matches that of real subatomic particles. So let me just highlight again. They're fictitious and easier to work with, and their collective behavior matches that of real subatomic particles. So the problem is, if we call it fictitious, can we say it's, can we actually say it's real? Okay, so there's a problem with the choice of words. We have lots of things called fictitious forces in physics. I'm told by one physicist that gravity is a fictitious force, which is kind of hard to believe. He and I had an argument over that, and I said, okay, you're the senior physicist. Gravity is a fictitious force. Like, okay, I never heard it put in those terms. In physics and in the military, you have fictitious forces that are very important, like the Coriolis force. It's not like, they'll say it's a fictitious force, but it has real effects. If you fire an artillery shell or launch a missile, you have to account for your position on planet Earth, because you'll have the fictitious Coriolis force making your missile or your artillery shell move somewhere. So it's like, okay, our fictitious force is real. Okay, this is a semantic game, or semantic. It's mincing words. It's semantics, because you have to account for it. When I was in the aviation defense industry, when we're modeling the Harpoon missile, when the pilot is setting up to launch and attack a ship, he has to enter Coriolis force parameters. Same for artillery. So if they use the word fictitious, it's like, okay, But the nice thing is we can model these fictitious particles as real particles, and we get real results. So maybe that's about the best that I could do. So let me read Reasons to Doubt. He said, and did my stream just die? Okay, he said, but that's a very cursory search. I've never heard of them before. So they basically doing physics like an engineer. I like it. And he says, that makes a lot of sense, thanks. All models are wrong, but some are useful. So I asked, did my stream just die? Okay, still working. All right. We just might be having a few slowdowns. Okay, praise God. So, all right, guys, independent of whether you're into young Earth creationism or not, I hope you've been able to come out of this feeling like you've learned some interesting physics. And particularly for Jordan, who loves nuclear physics, I hope this is, even if you don't accept it, I hope at least the things you've learned as I read this paper have been kind of new frontiers in understanding the world. So this is now where the condensed matter physicists and quasi-particle physicists are now suggesting that it could have influence on nuclear reactions. And I will say this, the NASA research on the mixed energy nuclear reactions are basically invoking some sort of large-scale quantum effect. They call it electron screening. Electron screening is kind of more like a general, it's not at the particulate level where you can model individual particles. So this is a step, a further step. But the NASA, and I covered the NASA experiments in mixed energy nuclear reactions, they're able to lower the Coulomb barrier in the solid state. But they weren't invoking quasi-particles to explain these nuclear reactions. The important thing is NASA has affirmed that these reactions are real. They're getting nuclear reactions at lower energies. It's still high energy and mixed energy, but it is lower energy and it is in the condensed matter state. So we're definitely now, NASA is saying we're able to get condensed matter nuclear reactions, and they are slightly lower than high energy. The Coulomb barrier has been lowered. But now this is a step further. These are discussing reactions that haven't been yet accepted by the mainstream. So now let me go back to where I was. Okay, I'm just going to read through this. The Robertson-Schrödinger relation relates the variances of momentum and position relative to the center of mass and momentum XO and momentum PO. And I'm not going to read that equation. Where H is the reduced Planck's constant and Kn, K function of n, is a form factor obtained by solving the Schrödinger equation. Let me get back my figure 1 shows the potential versus ion separation distance for sigma x for a tri-body including attracting reactants and normal electron. The curve below the axis is negative Coulomb attraction, and the dotted curve below is the axis. Above the axis is repulsive, the Heisenberg and center uncertainty principle, the HUP. How can we use solid-state electron quasi-particle and thereby take advantage of an elevated effective mass? The condition for validity of the electron's effective mass demands that the electron be non-interacting. In a conducting solid, electrons and reactants have quantum expected positions at the equilibrium regions, equal forces in all directions, even though the equilibrium is unstable. This position is non-interacting. I don't quite understand what that means, okay? Like much of this paper. A sufficiently heavy electron sluggishly moves in response to nearly equal forces in opposing directions. Again, when they say heavy electron, this is a heavy electron quasi-particle. It's not a real electron. It's a fictitious electron. If the two reactants approach to within the force of their binding potential before the electron, or muon, moves away, they may promptly bind and share the energy with the third body. If instead the third body moves away first, the Coulomb collapse fails and no reaction occurs. Okay, so they're describing the conditions where you can have Coulomb collapse, and they did cite, again, the case of muons, which isn't, I don't know about muons in the condensed matter state. Okay, so guys, they're obviously, to me, it seems, they're referring to experiments that are well known, that they don't even cite it. So well known in their community. So let me just continue on here. So this is we're getting classical mechanics, we're getting quantum mechanics, we're getting nuclear physics, we're getting solid state physics. and nuclear physics all into one. This is just like science at its best, guys. Quantum mechanics readily approximates these two situations, as explained by comparing Figure 1 and Figure 2. Figure 1 shows a state with normal electron mass, where electron tunneling always finds no stable states at small sigma binding dimensions. Again, sigma, I guess, is, you can kind of describe it as kind of a volume. All right. So when they say sigma, I think that's kind of a volume, a probability volume. Correct me, guys, if I totally messed my quantum mechanics up here. But the large increase of quantum kinetic energy confinement, the dotted line at small sigma x, overwhelms the binding potential, preventing a reaction. So they're describing then why a real electron does not bind. A heavier electron mass can reduce the quantum kinetic electron confinement and yield diagram of Figure 2, where tunneling can occur. Okay, so now I'll direct the diagram here. This should be familiar to some, it looks like some nuclear physicists would understand this. And I'm sorry that this is jumping all over the place. So they're describing why the electron, I'm just going to invite the readers, interested readers, to look at the paper here, but this is describing why the electron is not going to bind. I'm presuming this is the proton here. The potential energy is still potential binding energy still cannot be resolved with real electrons. And if I'm not stating this correct, the paper is the correct reference. All right, is the original source. You can read it. So it says here, potential curve with normal electrons. The total QKEC is about 200 mega electron volts repulsive in the nuclear region, much larger than the reaction's nuclear binding potential, which is 3 to 12 mega electron volts. Therefore, binding with normal electrons has vanishing probability. Oh my goodness. So this explains this is the more formalism of why electrons don't collapse into the nucleus. Oh my goodness, and Mr. Jetty here. I think the case of the electron is real, but the mass is fictitious. Okay, so we got a nuclear engineer and reasons to doubt here, and Mr. Jetty here, he's someone who works on a particle accelerator. Oh, by the way, Mr. Jetty, earlier in the show I talked about quasi-particle colliders. They now have quasi-particle colliders. I don't know that they would call them accelerators, but the quasi-particles collide, and they create an energetic release of photons, which I think is really cool. I cited it earlier in the show. So what they're saying here is this is one way of mathematically showing why real electrons will not have a nuclear collapse into the positively charged nucleus. But they say then the quasi-particle can, and they're describing it here. So they say potential versus ion separation distance, sigma x, for a case with a heavy electron quasi-particle. The tri-body comprises negative electrons and reactant ions, O, attracted together in a three-body state initially of chemical size, A. If the electron mass is heavy enough, the electron can tunnel to the three-body state of binding size. The reactants are already in a state of Coulomb attraction. Tunneling places the electron within the range of binding potential well at nuclear force radius. Tunneling results in prompt Coulomb collapse and reactant binding. For electron-stimulated transmutations, the binding potential is nuclear, and the tunneling is to the nuclear force radius. That was what I was looking for, guys. I kind of intuitively said there's a possibility here, but this guy, who apparently had worked at UC Berkeley and Santa Barbara, kind of in their I guess in their nuclear research, he was kind of the pioneer of this. Oh, and Mr. Jetty said, for this you need a solid state physicist, not me. And Dr. Charles is probably, God bless him, he was my professor of solid state physics. That wasn't one of my better classes, and now I feel bad I didn't take solid state physics more seriously. So yeah, there is a lot of solid state physics at my alma mater, and yes, some of my professors are either happy with me now or just cringing. So, but this is so cool. This is something I did not. This is something I actually, with all the graduate level physics I had, if someone asked me, Sal, why does not the electron collapse into the nucleus? I could not answer. I'm just like, well, I would give the answer like my Dr. Treffel gave me, was in my undergrad. It's like the moon. The moon can orbit. It has that velocity, therefore kinetic energy, and unless you can reduce that kinetic energy classically, it's not going to collapse into the Earth. In fact, we know from orbital mechanics, it looks like the moon is actually receding away. And orbital mechanics is another tough classical question. Now, in the quantum world, you don't have those nice gradations of orbits. You have discrete energy states. That was the Bohr atom, which is semi-classical quantum mechanics. That was superseded by the formalisms of Heisenberg, and that's where it gets a little hairy. But you can kind of qualitatively say, okay, you have these orbital energies, therefore you don't get collapse into the nucleus. And then they just described it in terms of Heisenberg uncertainty principle and this quantum kinetic energy of confinement, which I actually never got in my quantum mechanics classes. I have Patrick says, this is not your normal undergraduate physics stuff. Okay, so even though I took graduate quantum mechanics, they actually didn't even go to this level where they talked about quantum kinetic energy of confinement and the Heisenberg uncertainty principle in the way that they do this with all these energy diagrams. Okay, but qualitatively, I'd say it parallels the idea of the moon orbiting the Earth. When you have kind of that orbital energy, it's not going to collapse into the Earth. And that's just a really gross simplification, and there are some limitations to that when you try to extend it to quantum mechanics. So the formal answer is right here. So I'm just trying to give a dumbed down version of it just so I can understand it a little bit. So this is basically what they're saying. You can reduce the mass and therefore it's kinetic energy, because classically kinetic energy is 1/2 mv squared. We're still talking non-relativistic, so we can use that formula. And so then they're showing here clearly when you have this, when it goes below the x-axis here, I think that means you can get binding, whereas normal electrons, real electrons, don't bind. Let's see if I have it. The real electrons don't bind. You want the electron to go below the x-axis to merge with the proton or the positively charged nucleus. Now the quasi-electron, which is not a real electron, it can bind. Okay, so it doesn't physically change the nuclear structure. What it does do is reduce the Coulomb barrier. And so it is, again, you can merge quasi-particles with real particles, which is really cool. So we're merging quasi-particles with real particles. So I'll just go on here. If the electron quasi-particle has an effective mass, then the quantum kinetic energy of confinement is reduced, and the nuclear binding potential may be so low, may be low enough to form a stable potential well in the nuclear region. the electron tunneling through the KQEC barrier becomes feasible. At threshold, the potential well of figure 2a dips below 0 and is therefore stable. Prompt, oh my goodness, that means this quasi-particle is just going to be following it along. Prompt tunneling may occur, resulting in bound nuclear states, with third bodies redistributing the excess binding energy. So now we have this neutral nucleus just floating around in the solid state. Well, in the solid state, it doesn't really float around. It just stays there. That was important. Effective mass threshold. If the effective mass forces of Coulomb potential plus binding energy can exceed the KQEC at the nuclear force radius, then a stable potential well forms, and a nuclear binding reaction is possible. And I'm not going to read the equation, you have it there. Methods for producing the heavy electron quasi-particles are discussed next. The estimates of threshold effective mass, that's m star, range from about 9 MO for deuterium reactions and up to 90 MO for hydrogen reactions. MO is the normal electron rest mass in a vacuum. Yeah, that's an O, not an E. Okay. O, M naught. Generating heavy electron quasi-particles. The effective mass of an electron quasi-particle in solid state physics is m star, and that's H is Planck's constant. I'm just going to, you can read what that says. Where E is the energy, K is the crystal momentum in the band structure diagram, and H bar is the reduced Planck's constant. Heavy electron quasi-particles can be generated by injecting crystal momentum K and energy E into crystallite lattice to place some electrons near inflection points of the band diagram. Oh boy, they're talking about Fermi level. All right, this is, okay, that's, oh boy. I may or may not have learned what that was. Okay, figure 3, energy versus crystal momentum is in a hypothetical band structure diagram of a solid crystal shown in the first Brillouin zone BZ1. Okay, now we're getting into definitely nerd torture territory here. This is showing how difficult solid state physics is. So I'm going to just pause here and read the side chat. Okay, so Mr. Jetty says, no, the electron in this paper is real, but it behaves as if it was much heavier. And Mitchell says, when observing electromagnetics, we have no idea what it's ultimately made of. Show me a particle from a simple magnetic field and I'll believe you. Until then, it is pseudoscience. Okay, well, thank you for your comments. And I'm just, so far everything I've read looks like mainstream physics. Accepted mainstream physics. I mean, I have read papers on heavy electron quasi-particles. So there's no question that they exist. Where this paper goes farther is saying when the heavy electron quasi-particle combined with a positive nucleus. So as far as I know, everything they have said is accepted physics. The part that is still can be argued to be contentious is whether it can bind to the nucleus. But I like it when you don't get, the math doesn't look too horrendous at this point. It looks very straightforward, and I like it when it's simple like that because it becomes more believable. Because sometimes there can be a lot of mathematical theatrics, and I saw that a lot in evolutionary biology where it's just garbage, and when you realize after you've read it all it's just garbage, then you're like, yeah, pseudoscience. But the math here is, at least so far, there's just a lot of algebra, which I like, okay? So we're not doing lots of differential equations and calculus yet. Nor even quantum operator calculus, what they call operator calculus. There's still a lot of basic theory, and that's reassuring. Okay, so I'll just proceed. In some lattices, thermal energy is sufficient. Crystal momentum may be injected by means as illustrated in figure 4. So, oh my goodness, this is for you, Ben Rex. You have a little battery there, atomic hydrogen and glow discharge ionic hydrogen, sputtering, dissociative absorption molecular hydrogen, electrolysis, the chemists will love that, ion guns, disintegration by heat, laser, etc. Methods of crystal momentum injection. Oh boy, this is really exciting. Okay, from the perspective of what can happen, and I'll relate to some experiments, there is the claim then that, okay, maybe an earthquake can cause nuclear transmutation because it can generate electricity. It can get in the crystal lattice. Now, this may lend some vindication to the infamous Bockris experiments at Texas A&M University, and I covered Bockris. He's a distinguished professor of physical chemistry. He had these little what he called coffee pots, where he put explosives in, and he was able to manufacture trace amounts of gold and other heavy elements. He sent it off to the lab. He has 200 peer-reviewed publications, distinguished professor of physical chemistry, and people were just like, you're nuts. You can't take a chemical explosion and do transmutation. This is like old-fashioned medieval chemistry. If the explosion created some sort of electricity and he did have crystalline things, it's possible then he's injecting the very things that can cause this condition of creating heavy electron quasi-particles. Now, he only got trace amounts. It's not like he set off the explosion and got gobs of gold. So the way to do this experimentally is you make sure you take your reactants, send them off to the lab, and establish you don't have trace amounts of gold. Put them in your reaction vessel, and you're hoping your reaction vessel doesn't have gold. You blow it up, what we call the coffee pot explosions. Then you send off the products to the lab and say, okay, do you find trace amounts of gold? That's what he claims. He got censured by 26 of his colleagues said, you have to stop calling him a distinguished professor. We don't accept him anymore because he's making these experiments. But he was a distinguished professor. 200 peer-reviewed publications. By way of comparison, James Tour has like 700. 200 is respectable. Okay. Me, I have my measly 3. Okay, so let me read Reasons to Doubt. All right, well, I won't have to read that. That was just between Mitchell and Reasons to Doubt. So it's heartening then that I have at least maybe an explanation for the infamous Bockris experiments, because what's described here then makes it feasible to happen with ordinary matter in an earthquake. Okay, so again, you'll just get trace amounts. You're not going to get large conversions. And it may explain why Vostovsky is claiming that he's getting nuclear transmutations in biological organisms, notwithstanding that, again, Jordan here had pointed out he had some concerns about the paper itself. And so in the interest of full disclosure, I'm just saying, okay, that I have to acknowledge that to be responsible. Okay, so he says here, all the observed transmutations known to us have a momentum injection trigger. Even clumsy injection results in a spread of crystal momenta and electron energies near inflection points, where some elevated effective mass electron quasi-particles are created. Figure 5 shows an inflection point in the band structure curve. Electron quasi-particle effective mass is proportional to the inverse curvature, which becomes very large at zero curvature inflection points. And for the interested ones, they can read this. And I actually don't know what the Brillouin zone is. I think that's a famous scientist. The crystal momentum wavelength must be short enough to access inflection points in the Brillouin zone of the crystal region. Short means a wavelength of no more than several times the unit crystal dimension. All the simulation methods of Figure 4 may be tailored to satisfy this condition. The reacting system must tunnel to state whose size sigma x is small enough for nuclear binding forces to have effect. The collapse must occur before the electron interacts significantly, collides. The simplest case evaluated here starts with an electron exactly at the equilibrium point. The collapse occurs to inside the nucleus. When the electron collides with the reactants approaching it from opposite sides, it can no longer use the lattice resonating property to provide an effective mass. It responds like a normal electron and scatters. So they had mentioned earlier in the paper the idea of resonance. So vibrations can play a role in this, which is interesting. There was a claim of sonoluminescence. Most people think it was a fraud, but sonoluminescence was studied by Julian Schwinger, who's a Nobel Prize winner. He won it jointly with Richard Feynman on development of quantum electrodynamic theory. He was a big advocate of cold fusion. They wouldn't publish his papers, but it's like, this is really terrible. You've got someone who won. He defined the field of quantum electrodynamics, and you're not going to let him publish. That's travesty, in my opinion. He could be wrong, but let him publish. He's earned the right. He also studied sonoluminescence, where water can vibrate, bubbles can, or something to do with bubbles in water, they can vibrate, they can release light. So this would be in the kilo electron volt range, I believe, some of the emissions. I could be getting this wrong. Correct me if I'm wrong. But you will get visible light, which is in less than 10 electron volt range. But the thing is, the vibrations are causing this energetic burst of light, and we actually even see it in biological organisms. So this could be a mechanism of injecting tunneling in a condensed matter state. Now, the liquid state is not crystalline. Liquid states are nightmares for physicists. Okay, I don't know that anyone could model this like we're doing here. We just have to decide if it can happen experimentally. So someone at Oak Ridge National Laboratories claimed that he got acetone that was enriched with deuterium in a sonoluminescence experiment to create fusion. The experimental apparatus has been debated, but now I'm getting a little more sympathetic and say I'm going to give the guy the benefit of the doubt. He might have actually found something. So yeah. So we're getting into some really cool stuff here. This is just a great paper on nuclear physics, quantum mechanics, solid state physics, even a dash of classical. We've got it all in this paper. This is so cool. All right. When the electron collides with the reactants approaching it from the opposite sides, it can no longer use the lattice resonating property to provide an effective mass. It responds like a normal electron and scatters. In the chemical counterpart reaction, the electron is ejected and shares the binding energy with the product nucleus left in a vibration state. However, in the nuclear transmutation, case, an ejected electron with binding energy 6 to 12 mega electron volts has not been observed. Only the expected product in its ground state is observed. Okay. don't quite know the significance of that. With a heavy electron quasi-particle, the chemical separation distance is shrunk by the square root of the mass ratio, where m, the effective mass over m naught, which is, I think, the rest mass of a real electron. Okay, so we call the tunneling region inside the minimum chemical separation the halo region, which may be on the order of 3 to 10 nuclear force radii. One can associate this state with a helium nucleus excited to the point of dissociation, a Rydberg nucleus. This state is created by the reactants converging on n pairs of heavy electrons. Whoa, n pairs, cool! The binding energy would be sufficient to disassemble the product into the original reactants. The compound nucleus in the halo region often fissions into stable fragments, such as helium. Oh, whoa. The compound nucleus in the halo region often fissions into stable fragments, such as helium. All right, this is totally new to me. We're getting a fission reaction without a neutron. Whoa, okay. We're getting fission and fusion with these heavy electron quasi-particles. Independent of whether you guys are young Earth creationists or old Earth creationists, I just want to praise the Lord here, because the universe he made is just so cool. The portion of the electron wave function reaching the nuclear radius provides transient shielding that enables merger of reactant nuclei. Prompt Coulomb collapse can occur if one or more additional bodies can absorb binding energy, also conserving momentum and spin, or if the reactants fracture into fission products. Oh, by the way, I think there was an allusion earlier to fractional spins, or I think that might have been in another thing I read here. I think that's referring to things like the fractional quantum Hall effect. I could be wrong. Anyway, the tunneling probability is estimated to be this. It says where the Gamow factor is that. Oh, the first time we have actually an integral so far in the paper, a definite integral. I'm not going to read that. Okay, X represents sigma X. A is the nuclear force radius. B is the chemical separation distance. This is a three-body tunneling at thermal conditions, not two-body tunneling as in hot fusion. Okay, so wow. So there's a probability in hot fusion, it's two-body, where you just have them coming together in the same plane. No, I'm sorry. It's still in 3 dimensions. It's 2 bodies. Okay. Hot fusion, you get 2 nuclei and they collide. It's very easily modeled. But in hot, three-body tunneling is complex. Okay. A review of 30 years of isotope data show if we use pairs, for example, n pairs of protons, deuterons, and tritons, we can account for almost all of the isotopes observed. N pairs plus a central reactant plus heavy electrons equals transmuted nuclei, internal energy, and dissociation products. Oh, and Cheryl is here. Greetings. Welcome to our nerd torture session. I'm in nerd heaven. This is not torture for me. This is so fun. We're going on almost 2 hours now, and we're not even halfway through the paper. This makes me just want to sing. Reminds me of the song in the Broadway musical, My Fair Lady. I could have danced all night. I could have danced all night. Well, I could read this paper all night. It's beautiful. Okay. So he says we use the notation H2. By the way, this is really the first time I'm reading the paper methodically. So that's why I'm really excited. There are gems in here I didn't see earlier. We can use the notation H2 to represent a pair of H atoms in the lattice, keeping in mind that this is not a gas molecule. An example reaction is, and that's it, H2 plus nickel plus 2 heavy electrons equals zinc. And this is going to be significant. Oh yes, Cheryl, you missed me singing today. I did a poetry reading this afternoon, testing out. And so if you look that up, you'll get me singing at the end. So yes, this channel is probably the most, you'll definitely get variety on this channel for evidence and reasons for the Christian faith. Get me doing nuclear physics and condensed matter physics and quantum mechanics and singing Broadway musicals at the same time. Actually, Cheryl, since you're here and you're the one lady in the chat, I sang from the Broadway musical Carousel. It goes, I sang a passage. It goes, "If I loved you, words wouldn't come in an easy way. Round in circles I'd go." Okay, so back to, that was a little bit of a nerd break here. Back to serious stuff. We used, okay, so this now is how we can convert nickel and hydrogen into zinc. The zinc may then fission into various branches discussed later. So this is figure 6, and they describe here the lattice. I believe this is a nickel lattice. So if you have nickel, I don't know if it forms, I'm assuming this is a nickel crystal. Let me just see this. Okay, so we have hydrogen that's pumped into nickel, and then we inject a disturbance to give it that crystal momentum. So here we have the nickel reactants, the H atoms, and heavy electron quasi-particles in a crystalline lattice serving as a reaction region. The blue circles, they look like black and white here. Sorry, they are very faint blue circles. Normal electrons are not shown. Okay. So we have all these heavy electron quasi-particles, the EHs, and then you have all these reaction regions, which are the little circles. And so these electron quasi-particles get around the hydrogen and nickel atoms. And these are atoms. This is not the plasma state. And the quasi-particles would then collapse or get involved in some sort of interaction binding to some of these nuclei. Wow. And then you get zinc. Electron quasi-particles experience on average equal forces in all directions. The quantum expected position values in the crystalline approximate non-interacting particles. A conducting crystallite approximates a resonant chamber. Phonon lifetimes of approximately 3 picoseconds. Okay, phonons. This again is in solid state physics or condensed matter physics. By the way, because this is so bizarre with these fictitious particles that are actually have real, fictitious particles have real effects. Maybe that's the way to describe it, which is really kind of a cool way of conceptualizing things. Fictitious particles, quasi-particles, have real effects. We also have these things called phonons. So you've heard of photons, where energy is released into a photon, electromagnetic emissions. Vibrations can absorb energy in discrete packets. So you may have a crystalline lattice, and it will actually absorb energy. A photon can enter the crystal. Okay, this is where my quantum mechanics is a little fuzzy. So let's say you have like a photon interacting with a black body. say a piece of coal or whatever, or let's say a crystal. That's better, a crystal. If a photon hits a crystal, the crystal will start to vibrate. So it's getting a discrete energy packet. And so those discrete changes in the overall energy, the vibration, are called phonons. So I would presume then that you can get phonons to convert into photons, which would be a black body radiation, or the reverse. And my professors are probably cringing if I mischaracterize that. So I invite people to correct if I got that wrong. So you're getting the word phonon here. Phonon does have a correspondence to photon. I think it deals with vibrational energy. Phonon lifetime of 3, approximately on the order of 3 picoseconds, for the expected ballistic lifetime of the electron quasi-particle, which is on the order of 10 femtoseconds. So the phonon lifetime is long enough to support many generations of heavy electron quasi-particles. The duration of the heavy mass approximation must be at least long enough for the reactants to undergo Coulomb collapse to binding. Estimates show both the chemical and the nuclear transmutation cases have sufficient duration for neighbors to tunnel and bind. By the way, this is the best article on cold fusion I've ever read, and it's been critically acclaimed in the low energy, the leaner community, low energy nuclear reaction community. Are the heavy electron quasi-particles paired, that is spin up and spin down? Figure 7 lists some, I guess that's a rhetorical question. Figure 7 lists some transmutations that have been reported. So now the experimental evidence. N-D pair reactions observed. I don't know what N is. D2 is, I think, deuterium. So we get calcium to titanium. Don't know what W is. I don't know what OS is. We get cesium to PR. I don't know what PR is. And I presume that means it gets a 50.6 mega electron volt release. Deuterium and strontium gives MO. Is that molybdenum? I don't know what W is. Anyone feel free to look that up on the periodic table. W to PT, I don't know what PT is. We have barium to samarium. Titanium to Cr, don't know what that is. Titanium to iron, which is Fe. Titanium to nickel, and titanium to zinc. W is tungsten. Thank you. Thank you, guys, and thank you, Patrick Alexander. The N pairs of hydrogen isotopes bind with a central reactant to form observed products. The estimated threshold effective mass for D2 reactions is M star on the order of 10 electron rest masses, and for the reaction, for H2 reactions of the effective mass on the order of 35 electron rest masses. So I think M star refers to the electron quasi-particle. So the electron quasi-particle has an order of 35 rest masses of real electrons. For simplicity, the electrons are not shown explicitly in the equations. Various paths. Okay, it's going funny on me here. Various paths are possible for the compound nucleus to conserve hadrons, energy, momentum, and spin. And this is where we get into nuclear physics. There's something like the hadron number. There has to be hadron conservation in a nuclear reaction. Okay, that's the nuclear physics, which I have cursory understanding. Various paths are possible for the compound nucleus to conserve hadrons, energy, momentum, and spin. So we need to have all these constraints of conservation where we conserve hadrons, energy, momentum, and spin. Reaction paths may include emission of energetic electrons, neutrinos, gamma rays, or X-rays, internal excitations, and fission, fracturing into stable fragments such as helium. For a given primary reaction, we can estimate the required mass threshold, m star, identify possible reaction products, estimate tunneling probabilities, and calculate energies available for each path. We compare model predictions with experimental data of transmutations. We are not able to compute reaction rates and branching ratios. Wow. Not everything, but there's plenty there. Fission products. The collapsing reactants in electron quasiparticles have an approximately Rydberg state with chemical size greatly reduced by heavy electron screening. Collisions may terminate an electron's heavy inertia, but the three-body size may already be small enough to facilitate tunneling the rest of the way to nuclear dimensions from a halo, that is a cloud of particles like a compound nucleus. The nucleons arrange into stable fragments that may promptly fission. Whoa! Okay, we can estimate which fracture products will be stable. So we can get fusion and fission with these quasi-electrons. We are changing nuclear structure at low energies. And low energies, the quantum momenta can be induced by just like collisions. So that Bacchus experiment is looking more promising. And there is something that Nature, the journal Nature, let me see if I could find this. If you'll indulge me for a moment here. Nature, fraud. There was an Italian experiment. I'm going to look this up. There was an experiment where they took granite. Okay, so you young Earth creationists are fascinated. Where they were able to just compress granite and they were detecting neutrons. So again, this theory, if true, and it, again, these are researchers that have worked in this, and they're more because of the experiments at NASA on mixed energy reactions, and then combined with muon-catalyzed fusion, the fact of electron quasiparticles, you do have a lot of the elements there that would, if you can just connect the dots, then you can have these low energy nuclear reactions. I'm not gonna, I just did a quick Google. I couldn't find the article I'm looking at. There was a big scandal reported in the prestigious scientific journal Nature, where scientists claimed that they could do compression. And for mechanical engineers like Jordan Kay, you'd appreciate this. It's when you got to certain levels of strain. And I'm not really good at mechanical engineering or material science here. They're able to generate neutrons and claim transmutation. So now that they were kicked out of the university, they were disgraced. Their experiment now is looking a little bit more, there's reason to give them a little benefit of the doubt at this point, that they may have actually detected neutrons when they're doing compression experiments. This is just absurd to expect this. But now, as I said, okay, the way we're going to settle this is with more experiments. But the thing that is reassuring now is I'm starting to see the theory, it's looking more believable now based on theory, especially with the advance of solid state physics, condensed matter physics, and the advance and the plethora of new quasi-particles, and being able to synthesize more and more of them and verifying them experimentally. Electron quasi-particles have been verified experimentally. The thing that this paper is going further is saying the electron quasi-particle can bind with the nucleus such that you can lower the Coulomb barrier and then get these both fusion and fission reactions. So let's just move forward here. And, you know, guys, I know this can be grueling to be going through this paper, but I figured since I want to read this paper anyway, I might as well just read it online and just kind of enjoy the party. So let's just go on here. N pairs of low mass isotopes are catalyzed by sufficiently heavy electrons to cause a rearrangement of the collective set of nucleons in the N-body cloud. The fission products conserve total hadron numbers. For example, H2 plus nickel-62 equals iron 56 plus 2 heliums and 3.6 mega electron volts. So I think that just means you conserve the number of nucleons. So helium has 4. 2 helium is 8. 8 plus 56 should equal 64. And so H2, yeah, okay, so H2, on the left side of the equation, we have 64 nucleons. On the right side, we have 64, so we've conserved the hadron number. I think Jordan probably bailed out, but is my math right there? Okay, has 30 protons and 34 neutrons, so that's 64. There's typically enough energy to rearrange the nucleons in the halo region, resulting in the observed fission products. These reactions release about 6 mega electron volts per proton or neutron taking part in binding. The binding energy of alpha particles is typically less than this for nuclei heavier than about iron, and it decreases to negative values for radioactive uranium and high mass elements as shown in figure 8. Okay, this is the alpha binding energy. Oh, this is significant, guys. I think the helium nucleus is an alpha particle. The helium nucleus is an alpha particle. And so we have not, this is not even nuclear decay. We've created basically an alpha particle without even nuclear decay. This is just so cool. Mitchell asks, why is the element of gold rare, yet it is close to the atomic weight of iron? That would be a Jordan question. Jordan has reasons to doubt. He's our resident nuclear engineer. He might be able to explain that. As you could see, all of this stuff is requiring knowledge from a lot of disparate fields. So anything involving compression and strain, Jordan also has I guess he had a dual major in mechanical engineering as well as nuclear engineering. Those are mechanical engineering terms, and how they can inject crystal momentum. That's crystal momentum is a solid state physics thing, so it's quasi-particles. But then you have the nuclear side, which thankfully Jordan is familiar with. And then you have all the quantum mechanics physics tied up into this. Yeah, this is just, yeah, this is not trivial, but this is actually a paper that's very readable. I mean, I read through a paper recently on this channel by Adamenko and Vostovsky. That was just so way over my head. That would have given me a headache. But this is a paper that's actually readable at my level, my low level of understanding. Okay, so now we'll go to the palladium and deuterium reaction products. We postulate that some of the formerly heavy normal electrons in the halo region attach to reaction products. This can produce energetic natural helium and single-charged helium, as well as neutral hydrogen, deuterium, and carbon atoms. Data suggests this happens routinely, and that this energetic neutral emission could be the dominant energy path. Deuterium reactions could be dangerous because natural helium project could be highly energetic, on the order of 23 mega electron volts, highly penetrating and difficult to detect. These are deadly gamma rays. You may not be able to block it. Whoa. Whoa, 23 mega electron volts. Okay, so your X-rays are on the order of, let's say, 30,000 electron volts. 23 mega electron volts per photon is tremendous. Your light bulb emits photons that are in the order of a few electron volts. Okay, so this is nasty. If these things go through your body, that's bad juju. The reactants apparently form halo nuclei in a system with sufficient energy to cause fission. Figure 9 shows fission products formed using ND2 fuels measured by EDX spectroscopy. I don't know what ND2 are. I don't know what the N is, okay? N, I think, could mean anything, any reactant. And EDX spectroscopy, EDX, okay, curiosity is going to kill the cat. I need to find out what EDX spectroscopy is. It's one way of detecting that you've actually transmuted a property. You transmuted a element. So thank God for Google here. Energy dispersive X-ray spectroscopy. So probably what they do is they put the deuterium and nickel and then, or whatever, they pump some electricity into this, and then they take an X-ray machine to detect if there is these transmuted products on the surface. So to do the experiment correctly, you'd make sure that you have the pure substance there. You'd probably do the X-ray spectroscopy, energy dispersive X-ray spectroscopy on it, establish that you don't have any of these products. You run the experiment, and if you detect the products, then you've had a transmutation. Okay. Energy dispersive X-ray spectroscopy. I don't know if I'm going to remember that acronym. So here are all the various reactions they've had. And oh my goodness, all right. So deuterium plus palladium equals aluminum and bromine, but a release of 3.1 mega electron volts photons. That is like deadly. So this may explain why we're not detecting certain gamma rays. These are so energetic we might not be able to detect them. And we're getting up into the 80 mega electron volt range. Oh yeah, these are deadly. Oh my goodness. I am not, at this point, given what I'm hearing, I probably don't want to be working in those laboratories. God bless these gentlemen who are doing it. I think they have to be a lot more concerned for their personal safety now. They're saying we weren't detecting gamma rays in this, so we're not going to worry about it. There actually may be gamma rays of substantial energy levels. 80 mega electron volts is gigantic. Okay, just to give a comparison, when you get into the giga electron volt range, you're needing these very big colliders. Now, the really big ones, the Hadron Collider, is in the tera electron volt range. All right, your light bulb's only making photons of a few electron volts. So just to give you an idea, this is bazillions of times bigger. So those are all the reactions there, and they seem to be experimentally confirmed. With deuterium and palladium, we have iron and chrome, and then we have deuterium and palladium. We get aluminum, bromine, iron and chrome and nickel. We also get nickel and chromium, iron and nickel, okay. a sampling of the fission products with ND2 plus, oh, okay, N is the number. Okay, they should use lowercase n. I would have an easier time. Plus palladium reactions, where energy dispersive X-ray spectrum indicates only the dominant isotopes. Experimental data are in boldface, Mosier-Boss 2014. Heavy electrons are understood but not listed explicitly in the equations hereafter. So we're just repeating all these transmutation experiments. All right. I'm going to pontificate a little bit just as a break, and I can't sing anymore because my throat is raspy. We're halfway through this. I might resume this session because we're already at 2 hours, and we'll just stretch out. That means we have another party if I do this to read the rest of this paper. This is actually a very readable paper for my level of understanding. Some of the stuff that what I mean by that is I open some of my physics textbook and I just get a headache. I just like, I don't think I can understand this. And these are classes I took. Like I could pull out my general relativity book and I'm just like, oh my goodness, this is hard. Or some parts of my quantum mechanics book. There's still stuff that I supposedly was on the hook for. I got an A in the class, but I never quite had a good grasp of stress energy tensors and general relativity. But all these experiments, so let me just, I think I'm just going to just decide to just close the stream shortly because we're at 2 hours. How does this relate to young Earth creationism? Erica, my dear friend Erica, she's not a Christian anymore. She used to be a young Earth creationist. She's an evolutionist. She's a primatologist. She's my dear colleague and friend. As I said, people can sometimes wonder why am I not at odds with some of these other people? If you're a graduate student, regardless of your religious views or even views on the creation evolution controversy, there is kind of a camaraderie there that we're in the same battlefield of graduate school and we're all suffering through graduate school. And so Erica and any graduates, and there are lots of graduate students here on my channel, they can appreciate. There's just an automatic respect if you identify yourself as a graduate student in the sciences, and particularly things like electrical engineering, physics, mathematics, biochemistry, whatever. They're notoriously difficult. And when you do that, it's like, oh, you're meeting a fellow victim. I mean, and so there's a bond that transcends kind of our different religious viewpoints and our views on the creation evolution controversy. Erica has rightly cited the problem of the heat problem, that it would be created by accelerated nuclear decay. All of this stuff now that we're studying is leaving a path open for low energy nuclear reactions to take place simply because of tectonic movement. The fallback, which I don't think is a great fallback, is Walter Brown and Brian Nichols' theory that involve high energy, where you either have triboelectric or piezoelectric. They invoke piezoelectric, but it could also be triboelectric effect, where you basically generate the equivalent of lightning bolts inside the Earth, or similar levels of potential difference, and that this can create transmutation reactions. This is well established. Electricity, you get up into the millions of volts range, you can generate you can generate what they call photonuclear transmutations. Photonuclear transmutations. Whether those photonuclear transmutation will create fusion or fission, I'm not going there. But that's still a high energy reaction. It's still feasible through like the things that might happen in Noah's flood. But it's going to be even more feasible if these reactions can be mixed energy, or even better, low energy, which is what we're covering. We now may have an avenue where simple collisions and the vibrations they cause can inject enough, what they call in this paper, crystallite momentum. When you inject that, you create these electron quasi-particles. The vibrations last for a little bit. They talked about phonons and how long that vibration will last. It's orders of magnitude long enough to let these electron quasi-particles to form that have a lifetime on the order of picoseconds. And then the electron quasi-particles can then bind to atomic nuclei and affect either fusion or fission. And this is really cool. We have a mechanism then for changing nuclear structure that might, and I emphasize might, give us the proportions of parent and daughter products that could give the appearance of age. And so this is a new day for young Earth creationism, because this has been a thorn in our side for ages. And God bless all of the physics students out there who may be listening live or by recording. This could be, now you don't want to be too overt because you might get kicked out if you identify as a young Earth creationist, but now you're motivated. I'm certainly motivated to study solid state physics with the goal of seeing if you can affect nuclear structure. If you can solve some of these problems and make clean energy or alternative energy, all the better. But even beyond that, we've just learned just really cool nuclear physics. Now, the Oclaw thing, I'm going to let Jordan talk about that. The young Earth creationists have also debated that, and that is also another thorn in the young Earth creationist side. And that I do know of a nuclear engineer on the young Earth creationist side that explored that. He came to different conclusions than the mainstream, but that is outside of my expertise. So this is great. We're starting to develop a community here on this channel where we have at least people that have expertise that's higher than the level of a used car salesman dressing up in a Superman outfit. I know that was a mean swipe on my part, but yeah, you know, this channel tries to take it to like the next several levels up in terms of technical depth, where we actually have, like, for biology and biochemistry, we have professors of biochemistry and biology showing up on this channel, and they're senior researchers. We're at least getting some people with the appropriate nuclear physics background, particle physics, and Mr. Jetty 8-9. We have occasionally have had a paleogeochemist in John B. showing up here. And last but not least, you have me, who's a retread in applied physics at graduate school, but so much of it I really didn't grasp, and I'm kind of relearning it now. So we're definitely up to another level, and the discussion is moving forward. We have more data. And yes, Jamie says, I came across this on my own accord, just the channel speaking of its fascinating existence from a secular perspective. I instantly thought of hydroplate theory. Hydroplate theory addresses the problem of Oclaw, and it contests the mainstream narrative. And Dr. Dan cites Oclaw, so does Jordan K, and so does Erica. And, you know, I'm sorry, I just don't have an answer for that because that's nothing I study, but we do have a community here that is certainly more qualified than a used car salesman dressing up in a Superman outfit. And you know, I'm going to get flack for this, but he has a community that follows him, just like they follow Kent Hovind. And I just say, you know, that is not the best science. And, you know, it's only, you know, in their mind that they actually sometimes think they really have a grasp of the nuances in young earth creationism. Intelligent design is a lot easier. It's so easy to argue. You win that all the time. Young earth creationism requires a lot more expertise. You're getting a sense here, as I've read this paper, the level of expertise that's going to take to win this debate in young earth creationism. You can't be doing it with what I call used car salesmen in Superman outfits pontificating on stuff that they don't know. It has to be at this level to make a credible case. And you know, the credible case against abiogenesis has been made several times over very well. People like James Tour, Change Tan, Rob Stadler, and even the secular world like Eugene Koonin and some other people that are pointing this out. This topic of radiometric dating is much harder, much harder. Don't trivialize it. And so I'm trying to show what the level of discourse that needs to be attained to prosecute this. Yeah, we could cite things where radiometric dating is unreliable, but there's still problems with the appearance of age in some of the parent-daughter isotope ratios, and also the absence of intermediate isotopes. We may be on the verge of beginning to understand what are probably stable nucleosynthesis pathways that will explain the absence of intermediate intermediate rate isotopes. And so I'm excited for this paper and all the experiments that have happened in the last 30 years that are making this paper viable and promising. And then also all the recent experiments in mixed energy nuclear reactions. And so this is a blessed day because I've been watching the creation and evolution controversy unfold for 40 years. And, you know, as I said, I used to be a theistic evolutionist. Now I am then I became a younger, old Earth creationist, then a young Earth creationist. So theistic evolutionist, old Earth creationist, young Earth creationist. And it's paralleled the developments that we've seen over 40 years in the scientific world. You know, when evolution looked and abiogenesis looked like such a done deal, to see it coming apart has been glorious. Now we're starting to see the Big Bang as a theory fall apart. We're also starting to see now possibly more ways to change nuclear structure than, you know, kind of the typical fission and fusion that we see in atomic and thermonuclear weapons. So this is great. So let me close out with something very dear to my heart, just not relevant to anything. It is the poem High Flight, written by Pilot Officer John Gillespie McGee Jr. When he was fighting in World War II. And he was also a poet. He aspired to be a poet. He's a great poet. There's this beautiful romantic music set to airplanes, and you'll see a T-38 trainer. I'll go with no. How about the F-104 starfighter? So we'll have a poem with romantic music and an airplane, and the poem ends. I stretched out my hand and touched the face of God. And so this presentation I give in sacrifice and honor to the Christian God. To him be the glory alone. And I thank you all who have suffered with me through this paper to to learn about maybe something that could solve a major problem in young Earth creationism, and then hopefully give us more reassurance that the Bible is the inspired Word of God. So thank you again, and what I'm going to show has often been used as the sign-off. Back in the day of pre-cable TV and when stations weren't running 24/7, some of the older people will recognize this. There's Bill Morgan. All right, so let me get this set up and we'll sign off.
I have slit the surly bonds of earth and danced the skies on laughter-silvered wings. Sunward I've climbed and joined the tumbling mirth of sun-split clouds and done 100 things you have not dreamed of. Wheeled and soared and swung high in the sunlit silence. Hovering there, I've chased the shouting wind along and flung my eager craft through footless halls of air. Up, up the long, delirious, burning blue, I've topped the windswept heights with easy grace, when never lark nor even eagle flew. And while with silent, lifting mind, I've trod the high, untrespassed sanctity of space, put out my hand and touched the face of God.